Opening scene, light music, quick construction shots, aerial views of modern buildings. Hello and welcome back to Civil Engineering Edge, the channel where we explore the extraordinary stories behind everyday materials of aerated concrete and how this lightweight building material changing construction. Let's dive in. Cut to host on screen or animated explainer. If you've ever walked past a construction site and seen large, pale blocks stacked like oversized sugar cubes, you were probably looking at aerated concrete in action. It may look lightweight and fragile, but don't be fooled. This material is a game changer in modern construction. Section 1. What is aerated concrete? Visuals. Time-lapse of AAC block stacking. Thermal insulation demo. Aerated concrete, or more accurately, autoclaved aerated concrete AAC, is a special type of concrete that's packed with millions of microscopic air pockets, making it look like a sponge, but function like a powerhouse. It's much lighter than traditional concrete, easier to handle, and surprisingly efficient at insulating both heat and sound. Cut to animation. Close-up of AAC block cross-section showing air pockets. These tiny air bubbles don't just make it lighter, they improve thermal efficiency, reduce structural load, and even enhance fire and pest resistance. It's concrete, reinvented for the modern world. Section 2. Why use aerated concrete? Visuals. Comparison between red bricks, traditional concrete, and AAC blocks. Unlike traditional concrete or bricks, AAC blocks are designed to do more with less. They reduce the need for extra insulation, cut down on construction time, and lower overall material use. That's why they're becoming the go-to choice for sustainable building projects. And yes, despite all the air inside, AAC is still incredibly durable, non-combustible, and perfect for earthquake-prone areas. It's innovation meeting efficiency. Section 3. A brief history of aerated concrete. Visuals. Black and white photos of 1920s Sweden, old concrete lab experiments. The story of aerated concrete begins in Sweden in the 1920s. Engineers were searching for a building material that was light, cost-effective, and more energy-efficient than the bulky concrete and brick materials of the time. Their solution? Injecting air into the mix, literally. Section 4. How is aerated concrete made? Visuals, animated factory process, live shots from an AAC production plant. Now, let's get into the how. Making AAC is a fascinating process that blends chemistry, precision, and a bit of steam power. Here's how it works. 1. The ingredients. We start with fine sand or fly ash, cement, lime, water, and a small amount of aluminum powder. 2. The reaction. When aluminum is added, it reacts with lime and water, releasing hydrogen gas. This creates tiny bubbles throughout the mixture. 3. Shaping the blocks. The foamy mix is poured into molds where it rises, just like bread dough. 4. The autoclaving. Once semi-hardened, the blocks are cut and placed into a high-pressure steam chamber called an autoclave. This process cures the blocks, making them incredibly strong while locking in their lightweight properties. Section 5. Where is AAC used? Visuals. Housing projects, schools, hospitals, commercial buildings using AAC. From residential homes and apartment buildings to schools and commercial towers, AAC is used across the globe for fast, efficient, and eco-friendly construction. It's especially popular in places with extreme climates because it keeps interiors cool in the summer and warm in the winter, reducing the need for constant heating or air conditioning. The future of building materials. Visuals. Futuristic buildings, green construction sites. Aerated concrete might look simple, but it's part of a much bigger shift towards smarter, lighter, and greener construction. Who knew air could be such a powerful building block? Outrow animation. Channel logo plus music fade out. Section 6. Why AAC is a game changer. Visuals. Construction workers lifting AAC blocks easily, trucks transporting large quantities. AAC offers an all-in-one solution to several construction challenges. Because it's so lightweight, transportation costs drop significantly, and on-site handling becomes much easier and safer. Visuals. Split screen showing temperature-controlled building with and without AAC. Those tiny air pockets we mentioned earlier, they're not just for show. They provide exceptional thermal insulation, helping buildings stay warmer in winter and cooler in summer, which often means lower energy bills and less reliance on heating or cooling systems. Section 7. The simple science behind it. Visuals. Ingredients laid out with labels: sand fly ash, cement, lime, water, aluminum powder. The recipe for AAC is surprisingly simple. It begins with a blend of fine sand or fly ash, cement, lime, water, and just a dash of aluminum powder. That last ingredient, that's where the magic happens. Animation. Aluminum reacting with lime and water. When aluminum powder mixes with calcium hydroxide from the lime, a chemical reaction releases hydrogen gas. This gas forms tiny bubbles throughout the mixture. As the gas escapes, it leaves behind a web of microscopic air pockets, and that's what gives AAC its unique structure. Visuals. Side by side of a rising cake and AAC expanding in molds. In a way, it's like baking. The whole mixture rises just like a cake in the oven, creating a solid, aerated structure that's full of strength but light as air. Section 8. From slurry to green cake. Visuals. Large slurry being poured into molds. Once all the ingredients are blended into a slurry, it's poured into large molds. Think giant industrial cake pans. The aluminum reaction begins almost immediately, causing the mix to expand, often doubling or tripling in size. Visuals. Time-lapse of mix expanding into a soft green cake. Within hours, it firms into what's known as a green cake, a soft, semi-solid block of aerated concrete. It's still fragile at this stage, but it's just right for shaping. Section 9. Precision cutting. Visuals. Robotic wires slicing large green cakes into perfect blocks. Now it's time for precision. The green cake is carefully sliced into blocks or panels using fine wires or blades. The goal is to maintain those delicate air pockets while shaping the material into usable sizes. Section 10. The autoclaving process. Visuals. Blocks being loaded into massive autoclaves, steam and pressure indicators. This is where the real transformation happens. In a high-pressure steam chamber, the sliced blocks are stacked and loaded into the autoclave, where they're subjected to temperatures of 180 to 200 degrees Celsius and pressures between 8 to 12 bars. Animation. Chemical bonds forming crystalline structure. Under this intense heat and pressure, the lime and silica react to form a crystal called tobermorite, a compound that locks in the strength, durability, and fire resistance of AAC. Section 11. Final transformation and versatility. Visuals. Freshly autoclaved blocks being loaded onto pallets. The autoclaving process doesn't just harden the material, it stabilizes it, creating blocks that are durable, lightweight, and dimensionally precise. What comes out is a construction-ready product that stacks like traditional masonry, but without the bulk or back strain. Visuals. Various AAC block types, large, small, panel forms. AAC blocks can be manufactured in various sizes and shapes. Some are thick rectangular units for walls, while others are long, flat panels used in floors, roofs, or partition walls. And because they're so light and easy to cut, even with a simple handsaw, custom fitting on site is quick and stress-free. Section 12. Performance that speaks for itself. Visuals. thermographic images of AAC-insulated buildings, quiet indoor environments. What makes AAC a favorite among architects and engineers isn't just the convenience, it's the performance. The air pockets inside each block act like natural insulators, reducing heat transfer and muffling outside noise. That means buildings made from AAC are quieter, more energy efficient, and often require less evac power to stay comfortable. Visuals: mold-free surfaces, clean indoor spaces, pest-free home DMOS. And there's more! AAC blocks are non-toxic, mold-resistant, and pest-proof. They don't rot, they don't burn, and they're an excellent choice for everything from tropical climates to freezing winters. Section 13: Limitations and Considerations. Visuals: builder gently handling AAC, anchoring items carefully. Of course, no building material is perfect. AAC isn't as strong under heavy compression as traditional concrete, so it's usually not used for foundations or major load-bearing columns. And when it comes to anchoring heavy fixtures like cabinets or AC units, builders need to use the right tools and techniques, since AAC isn't as dense as solid concrete or brick. Section 14: A new way to build. Visuals: construction sites using AAC, before and after project results. So the next time you see those pale, puffed-up concrete blocks on a job site, you'll know exactly what you're looking at and why they're becoming such a popular choice worldwide. Cut to host on screen, smiling. Aerated concrete may not have the gritty toughness of old-school bricks or the sheer mass of poured concrete, but it doesn't have to. Its strength lies in balance. Lightweight yet sturdy, efficient yet dependable. Visuals: homes, schools, office buildings made with AAC. It's a material born of smart chemistry, thoughtful design, and engineering innovation, proving that sometimes the best building blocks aren't the heaviest, but the most intelligent. Section 15: Wrap up. Outrow visuals. Channel logo animation. Upbeat music. Whether you're constructing homes, offices, or classrooms, aerated concrete shows that lighter materials can lead to stronger solutions. Thanks for joining us on this deep dive into the world of AAC. Got an idea for our next video? Drop it in the comments, and we might feature your question next. If you enjoyed this video, don't forget to like, subscribe, and hit that bell icon so you don't miss the next episode of Civil Engineering Edge. Until next time, keep building smarter. Best uses, benefits, cost advantages, and conclusion. Aerated concrete, or AAC, is an incredibly versatile building material used in a wide range of applications, from residential homes and apartment buildings to schools, hospitals, and even commercial complexes. AAC blocks are ideal for non-load-bearing walls, floors, roofs, and partition panels. Visuals: different buildings made with AAC. Now, let's talk benefits. AAC offers excellent thermal insulation, which helps reduce heating and cooling costs. Its soundproofing abilities create quieter interiors, and it's also fire-resistant, pest-resistant, and environmentally friendly. Lightweight yet strong, it reduces labor fatigue and speeds up construction. When it comes to cost advantages, AAC might seem slightly more expensive per block than regular concrete. But the savings on transportation, labor, energy efficiency, and faster construction quickly outweigh the initial cost, making it a smarter long-term investment. Aerated concrete is more than just a lightweight alternative. It's a modern solution to traditional building challenges. Sustainable, efficient, and smartly engineered, AAC is helping shape the future of construction. Thanks for watching. If you found this video helpful, please like, subscribe, and click the bell icon so you never miss a new episode of Civil Engineering Edge. Got a topic you'd like us to explore next? Drop your idea in the comments below. Until next time, build smart and stay curious.